Okie doke. So today we're going to start our final exam review, second day, looking at nucleophilic substitution at carbonyl groups. And this is a topic that's really only covered in this class. It's not covered in Organic Chemistry 1 at all. But I wanted to start with question number 3 because this would have been covered in Chapter 20, because Chapter 20 covers carboxylic acids and their derivatives. And you can see we've got an amide, an ester, an anhydride, and an acid chloride. And it's just asking you which one of these is going to be hydrolyzed most slowly with sodium hydroxide. So if you were to treat any of these with sodium hydroxide, which one is going to break apart the slowest? Well, hopefully you remember that the most reactive of all of these, so most reactive is going to be the acid chloride, right? Those react really, really quickly. And the reason why is you have a dipole going this way, dipole going this way. And of course, a chloride ion is a very good leaving group. It's the conjugate base of HCl, which is a strong acid. So I'll put number 1 for this one, most reactive. And then we saw that an acid anhydride was actually second place in terms of leaving groups, right? A carboxylate, is it a good leaving group? Yes, it's not as good as a chloride ion, but it's still a decent leaving group. Then we looked at things like saponification and hydrolysis of an ester in acid, and we said, well, those are very effective reactions, but we said that an amide, as a matter of fact, does not hydrolyze very quickly. Okay, this is in fact the one that's going to react the most slowly of all. Amide hydrolysis is pretty terrible. Okay, it takes a lot of heat and a lot of energy because amides are just unreactive. Okay, so anyhow, so we covered that in chapter 20. So amides are going to be the least reactive. Acid chlorides are going to be the most reactive out of all of those. Okay, so question number 6 is again would be another chapter 20 question. It says, with which reagent is benzoic acid readily converted into benzoyl chloride in high yield? If you remember, in the textbook, there is a mechanism provided for this reaction. However, I told you you did not have to know the mechanism. But does anybody remember which one of these reagents would affect this transformation, taking a carboxylic acid and converting it to an acid chloride? Does anybody remember which one? Exactly. Thanks, Erica. It's thionyl chloride. So SOCl2, this is thionyl chloride. Thionyl chloride. Okay? And again, there's a mechanism provided, but you don't need to know that mechanism. Well, we've been talking about acid chlorides in the past, in the last 2 problems. So let's take a look at question number 8. And it said, what product would you isolate from these reactants? Now here we're taking an acid chloride and we're treating it with an amine. Now we know that if you want to react an acid chloride with an amine, based on what we covered in chapter 20, is that you actually need 2 equivalents of this. It's not stated, but it's presumed that you would have 2 equivalents. And without drawing a full mechanism here, you guys are all perfectly aware of that an amine is going to act as a nucleophile, and it is going to do a nucleophilic acyl substitution on your acid chloride. And so what's going to happen is basically the chloride is going to be replaced by the amino group, and then we end up with an amide like we see here in D. Again, there's not going to be this mechanism on the final exam, but the rationale behind using 2 equivalents of the base is that the second equivalent, I'll just scribble it down here, the second equivalent reacts with the HCl so that you end up with an ammonium salt, right? So that we don't just have an ammonium chloride salt. So we don't just have HCl kicking around in our reaction mixture. So the correct answer here would be D. So this is just a nucleophilic. So if you remember, this is nucleophilic acyl substitution is what we're covering right here, okay? If you need to go back and take a look at that in chapter 20. All right, number 10 is in the same vein. So number 10, if we scroll down here, what are the products of this reaction? So we just talked about the hydrolysis of an amide. So this is an amide right here, which you all know. So we'll put here amide. And you're hydrolyzing an amide in base, okay? Now, it's not a great reaction, the hydrolysis of an amide in base, but they want to be sure that you understand what products you're going to be getting. And so it might be handy to redraw the starting material, but to show some of the bonds that are in here, okay? And the bond that we're going to be breaking when we treat this with sodium hydroxide is the bond between the carbonyl carbon and the nitrogen atom. So when we break that in using a strong base like potassium hydroxide or sodium hydroxide, the cations are relevant. Okay, what are we going to end up with? We're going to hydrolyze that bond, and are we going to have an acid here? Are we going to have an acid? Well, of course not. We're in base. Okay, if we're in a basic environment, we're not going to form a carboxylic acid. We're going to form the carboxylate, and then of course an amine already is a base, and so we're going to form the free amine. All right, so that means that we're going to end up with C. We're going to end up with the carboxylate ion and the free amine. Now, the answer is not in here. It's not shown in here, but I just want to point out and remind you that if you're to take this compound and hydrolyze it in acid, on the other hand, in that case, you would end up with the carboxylic acid. Get it? You're in acid, so you get an acid. When you're in base, you end up with a base, okay? And then in this case, the amine would be protonated if you were in aqueous acid, so you'd end up with the ammonium salt like that, or the ammonium ion like that. Okay, that's if you hydrolyzed it in acid. So make sure you're aware of things like Fischer esterification, saponification, hydrolysis of an amide in acid and in base. Okay, let's move on to question number 13, which is a really good one. Question number 13 just says, which reaction sequence is preferred for this conversion? So we want to take propionic acid. So this is propionic acid, and we want to make butanone. Remember, it's not 2-butanone. That would be not butane. Butanone. 2-butanone would be redundant because there's only one place the carbonyl can be if you have a ketone. Well, if we did A, okay, I would really recommend against this because you're taking a Grignard and you're treating it with an acid. Well, that has an acidic proton. So in this case, all you're going to end up with is methane, which is a gas, okay? And then you're going to have deprotonated, why do I keep doing that? You're going to have having deprotonated the carboxylic acid, so you'll end up with a carboxylate and some kind of magnesium salt, okay? So that's definitely not going to do it. If we look at B, in B, after treating it with thionyl chloride, we end up with the acid chloride. So I'll use a bond line structure just so I don't run out of room. And then here we have a cuprate, okay? This is a cuprate, or we sometimes call that a Gilman reagent. And remember that, and again, this is covered in chapter 20, okay? In chapter 20, or is it chapter 21? Either that one of those, chapter 20 or 21, I can't remember exactly. But you end up adding to or displacing the chlorine with your cuprate. And so in this case, yes, we would end up with butanone. So this one had better be the answer. Let's just run over the other ones. The first, or C rather, if you have, the acid chloride and then you treat it with methyl lithium, what's going to happen is the methyl, which is an anion, is going to come in and it's going to attack here. You're going to do your nucleophilic acyl substitution, but then after protonation, you would end up with 2-butanol. You'd actually end up with an alcohol in this case, so that's not good. And then in the last one, I'll use my red pen again. First, you'd make the acid chloride with thionyl chloride. Then you treat it with methyl magnesium bromide. So let's say you treat it with methyl magnesium bromide. Well, the methyl is going to add, it's going to do a nucleophilic attack like this. We lose the leaving group. And then after protonation, from this one as well, you would end up with butanol. Okay, so the only answer here is going to be B. It's the only one where we make the ketone. So make sure you review this reaction, okay? Taking an acid chloride and treating it with a cuprate, like lithium dimethyl cuprate, which is what they put here. Then it only adds one, so it displaces the chlorine once. And there's no mechanism provided in the textbook for that. But remember that these cuprate slash Gilman reagent, okay? Those are important reagents, right? We covered those in detail. And so make sure you're aware of what a cuprate or a Gilman reagent does. Okay, moving right along. Give me a thumbs up if you're with me so far. Everybody with me so far? I'm just saying, I need a drink of coffee here, so. All right, awesome. It's fun doing a review. You get to see how much organic chemistry you know, right? Like this reaction here. We're taking this compound here, and then we're treating it with ethyl magnesium bromide. And remember that when you mix water in a proton, let me wait for my pen here, okay? So when you mix water and H plus, that's another way of saying H3O plus. Could I ask you, and this is not me trying to fool you or trick you or get you, what functional group is shown in this ring? What functional group is that? What functional group is in here? How would you describe that functional group? You got a carbonyl, then you've got an oxygen that is sp2 hybridized directly attached to it. Would this, does anybody have an idea what functional group that is? If I have this functional group, okay, if I have R, what would this be? Anybody? It's an ester. Thanks, Mustafa. Right, this is an ester. But when you have an ester, if when ester in ring, okay, then we call it a lactone. So this is a lactone here, but again, it's a type of ester, like Mustafa said. He's totally right, okay? So hopefully you remember that when you add your Grignard to an ester, it actually adds twice, okay? So in the first step, what's going to happen, if I just draw the ethyl carbanion like this, okay? In the first step, it's going to add, okay? So you're going to have something like this. And I'm not going to draw the whole mechanism. I don't have time for that. But if we just draw a partial mechanism, okay, you're going to have your ethyl group. Then you have your alkoxide like this. But then that's going to open up, right, like this, so that you end up with, you have a total of 1, 2, 3, 4, 5, 6, 7. So you have 1, 2, 3. That's supposed to be a double bond. 4, 5, 6, 7. And on the 7th day, you rested. No, I'm kidding. But anyhow, so we have the carbonyl here. And then what's going to happen is you have another molecule, or sorry, another equivalent of your Grignard, rather, is going to add again. Okay, so you're adding twice. And then after your proton transfer, well, which one of these compounds are you going to get? Well, you can clearly see that the answer must be, so put here keeps adding, and then you do a proton transfer, that the answer is D. So you add the ethyl group 2 times, okay? So if you need to review, I'll put a note here for you. It would be ester and ester plus Grignard, okay? And remember, we'll put here Grignard adds twice, 2 times, okay? It's a double addition. So it adds once, then you make a ketone, then it adds a second time so that you get an alkoxide, then it gets protonated to make an alcohol in the end. Okay, so that's a little bit of nucleophilic acyl substitution. I had chosen this problem as well, question number 15, which I think is an excellent problem. I really like this one here. Just questions that ask you, how would you make this amide? Like you want to take this carboxylic acid and you want to make this NN-dimethyl amide, okay? Like how would you go about doing that? Does anybody have an idea out of these conditions which one looks the most reasonable? I mean, if you just look at the first one, you take a carboxylic acid and you treat it with ammonia in the first step. Well, that's not going to do anything. The second one, it says to reduce it using sodium borohydride. Well, we don't want to reduce it because we want to keep our carbonyl intact. And then the last one is lithium dimethyl amide, which is just a base. So that one would just give you the carboxylate. All you would end up with in this case would be the carboxylate. So that's not really useful. But in A, right, in the first step, we treat it with thionyl chloride and we make the acid chloride. And then, so that's going to be, and then the next step, we just treat it with dimethylamine in excess, of course. You would use 2 equivalents or whatever, and then you would end up with your amide like that. So again, this would fall under the umbrella of chapter 20, okay, when we looked at nucleophilic acyl substitution. All right, cool. So addition of an amine to an acid chloride, we've already discussed that today. Like we've already talked about this reaction. This one is one that we've talked about as well, converting this to the acid chloride using thionyl chloride. So make sure you know those reactions. Okay, the next one is a reaction that we don't have a mechanism for in the textbook, but it is one that we went over a couple of times. We actually used it in a couple of practice problems where you take an amide and you treat it with lithium aluminum hydride. Since there is no mechanism provided in the textbook, the only way I surmise that you could remember this one is by memorizing it, okay? And so all that happens when we do this reaction is we just remove this piece here. We just remove the carbonyl and replace it with a CH2 group or a methylene group. And so we call this a reduction of an amide. So I'll just scribble it in here. Reduction of an amide. And so what we're going to end up with is just removing that group. So where's the compound? It must be D, right? That's all it is. Okay, it's nothing more than that. If you were to put the carbonyl here and erase these two hydrogens, you would end up with this compound. So that is how we know that it's just reducing, or that D is the right product. We just reduce the carbonyl. Okay, so there you go. So those are the questions that I had picked out from nucleophilic substitution at carbonyl groups. Now I want to move on to chapter 21, which is the enols and enolate chapter, right? Who remembers this one? Chapter, not 20, chapter 21, when we talked about enols and enolates. We talked about Michael addition, we talked about conjugate addition, 1,4 addition, 1,2 addition, cuprates, all this good stuff. And so it's important that you have some knowledge of enolate and enol chemistry. So let's start with question number 4. This is a compound that you recognize. This is diethylmalonate. We use this in a synthesis. And it says here, which set of reagents would best accomplish this conversion? Now, maybe if I draw the bond line structure of the starting material, maybe that will help. Okay, so here, no, missing an oxygen in there, Mr. Dion. Okay, there we go. That looks more like it. Okay, so we end up with this 1,3-diester here that we call diethylmalonate. So we have the diethylmalonate, and if you remember, if we wanted to abstract this proton here, what kind of base did we use? Well, we said we didn't have to use that strong of a base because the pKa of this proton is around 9. And so in that case, we can use a weaker base like sodium ethoxide, which is this here. So this is sodium ethoxide. And what that's going to do is it's going to rip off the other proton to make the carbanion, which is going to be stabilized by resonance. Okay, you can draw 3 resonance structures for that. And then in the next step, you're going to treat it with your ethyl bromide is what they have in the example problem. So just nucleophilic attack, loss of leaving group. And so the answer has to be B. It has all the right pieces. We do a deprotonation followed by an alkylation. And of course, this question doesn't even cover hydrolysis or anything like that. So it's just kind of understanding pKa and which proton is going to be abstracted. Let's move on to question number 8, which is way down here. All right, so let's see here. This one, it says, what would be the major product of this reaction in number 8? Okay, so now keep in mind, we're taking the aldehyde, okay, and we're treating it with hydroxide. And what we said was, if you do that, since hydroxide isn't that strong of a base, you're actually going to have a mixture of the aldehyde that's shown here. So I'm just going to leave that there. And then you're also going to have the enolate. So I'll just draw it like this to try to keep things consistent. So if you have a mixture of both of these, what's going to happen is the enolate is going to do a nucleophilic attack here, okay? And then after a proton transfer, you're going to end up with the beta hydroxy ketone or aldehyde. So if you look at these answers here, you can see that this one is wrong because you end up with a ketone. This one is just plain wrong. I have no idea why you would have an acetate or an alcohol. If you look at this one, you have the alpha carbon, you have the beta carbon. So there's the beta hydroxy aldehyde. And if we count the carbons for the first aldehyde, we have 1, 2, 3, 4. And if we count the carbons for the second one, we have 1, 2, 3, 4. So C definitely looks like the right product. And then if you look at D, well, that's just plain wrong. That would require making a carbanion down here somewhere, okay? So this is just going to be aldol addition reaction. So I'll put here aldol, or fighting to find my words here, aldol addition reaction, right? If we want to do an elimination, we usually use heat to do that. There's no mention of heat in the starting materials, and there's no products that would have come from elimination anyhow in here. So that's how you kind of cobble that all together into something that seems reasonable. Okay, after question number, that one, we have question number 11. Well, I didn't circle it, but question number 11. It's this one here. It says, what would be the major organic product of the base catalyzed reaction? So if we look at these two compounds, we have this aldehyde and then we have this ketone. There's only one enolizable proton in both of them, okay? You can't deprotonate the aldehyde proton. There's no proton here to deprotonate. There's no proton here, right? Because remember, C6H5 is the same thing as a phenyl group. So there's no deprotonation that's going to occur here. And so the only place you could abstract a proton would be here. So presumably that means that we're going to end up with some C6H5, and then we're going to have CH2. And so that's going to be our enolate. So what's going to happen is that enolate is going to be able to react with this aldehyde, and that's going to give us what? Okay, so if we take a look here, that means we're going to end up with something that looks like this, or something that's situated. So we're going to have C6H5, the carbonyl is intact, we have CH2, and what's going to be attached to that is this carbon. So if I highlight this carbon in green, it's going to be this carbon right here, but now instead of being an aldehyde, it's going to be an alcohol because you're doing a proton transfer, and then you're also going to have C with 3 methyl groups, like that. So which one of these fits the bill? Well, if we look at the first one, it's wrong. If we look at the second one, it's wrong. If we look at the third one, right, there we go. We see that D must be the correct answer because it has the right pieces. It's exactly what we had written above. So again, this would be another aldol addition, but this is an unsymmetrical aldol addition, okay? So this is not just your mixing the same aldehyde or just one compound. Question number 12 is another one that we went over detail. It says, which of these reactants can be used to make the compound shown by an intramolecular aldol reaction? So remember we talked about the intramolecular aldol. So this is where, if you think about it in terms of retrosynthesis, where you just use sodium hydroxide and cook it up, okay? So sodium hydroxide and heat. But I helped you come up with a sort of a way that we do the retrosynthesis, and this is our alpha carbon, this is our beta carbon, so it's to break apart or to size or to break that part of the molecule. And so we have 1, 2, 3, 4, 5, 6, 7. So if we make our chain, so which is going to look like, sorry I'm running out of space here, but it's going to look like 1, 2, 3, 4, 5, 6, 7. Okay, we can see that on carbon number 2, we're going to have a carbonyl. And on carbon number 6, so 1, 2, 3, 4, 5, 6, we're going to have a carbonyl that looks something like that. So that must be the starting material, is this diketone, which is B. You can see that that is the compound. Now, if you're wondering, well, why? So if I number these again, so if I number this 1, 2, 3, 4, 5, 6, 7. If you're wondering, well, why doesn't carbon number 3 make a carbanion and then attack here, and then I only have a 1, 2, 3, a 4-membered ring? Well, remember the 6-membered rings are preferred over a 4-membered ring or a 5-membered ring, and so B would be the compound that would make this compound. So this is going to be an intramolecular aldol reaction, but this would be an aldol elimination, or an aldol elimination, because we end up losing water in the process. All right, so hopefully my retrosynthesis here, you find that kind of helpful to steer you in the right direction. But I am talking too much. Let's move on to the next one I had, which was number 15. Yes, it says, which set of reactants in the presence of a basic catalyst can be used to prepare this compound. So you see that this is an alpha beta unsaturated ketone, right? This is your ketone. This is alpha. This is beta. And so if we have an alpha beta unsaturated ketone, we have to figure out what the base is that we're using, or no, not what the base is, but what the starting materials are, rather. So if we break the double bond, or if we think about that in terms of retrosynthesis, right? If you remember the retrosynthesis that I gave you before, is that we're going to have this ketone, right? So that's going to come from this part here. And then from this part here, we're going to have benzaldehyde. So we're going to have our aromatic ring like this. Then we have a carbon, and then we got a double bond like this. So benzaldehyde. And so based off of that, we can scratch off this one and this one right away. A and C both have benzaldehyde in them, but this one has acetaldehyde, and we need acetone, which is propanone. So this would be the correct answer. Again, what's going to happen is you're going to end up doing an aldol addition like this, followed by an elimination of water. All right. And if you're wondering, it just says here basic catalyst. It doesn't mention heat at all. The reason you wouldn't need heat in this case is because you make something. Look at this. You've got the aromatic ring that is conjugated. This double bond is conjugated, and this double bond is conjugated. So this is a highly conjugated system. Therefore, we don't need any kind of heat to drive this reaction to completion. So again, if you're struggling with questions like this one in my retrosynthesis, this is covered in depth in chapter 21. It's the enols and enolates chapter. There is quite a bit of chemistry in there, and like I said, one of the most difficult things about that chapter is finding the ways to connect the molecules or the atoms together. Okay, question number, did I really want to do question 18? Yeah, sure, I guess so. Anyhow, it says here, it's not that bad. If this steroid is heated up, which carboxyl group is going to be lost as CO2? Well, this is something that we talked about when we looked at diethylmalonate, right? If you take diethylmalonate and then you hydrolyze it, right? Let's imagine you have an R group here. You hydrolyze that, you end up with the dicarboxylic acid like this after hydrolysis. But then that ends up losing CO2, right? Then you lose CO2, and then it shrinks down to just this, where now you have the carboxylic acid. And so what do we have to have? If we go backwards, right, what do we have to have? We have to have some kind of carbonyl in the beta position. So if this is alpha and this is beta, and the only place that we see that kind of relationship is actually right here, okay? If you draw that ring out in more detail, look, you've got a carbonyl here, but then you have another carbonyl here, and then you have oxygen and then hydrogen like this. So this is alpha, you could say this is alpha, and this is beta. And so that is the only situation that arises here where we could see this decarboxylation, right? The loss of this piece right here. And so that is at carbon number 2. Okay, so carbon number 2. And so we're going to lose the carboxylate at carbon number 2. All right, everybody remember that decarboxylation? When we did it, we saw it in the amidomalonate synthesis, and then we saw it with dimethylmalonate as well. Cha? Anybody? I hope
Is
so.
this one also going to be covered in chapter 20 as well?
Yeah, this one actually came up twice. This came up in chapter 21, and it came up in chapter 25. So,
Okay.
yeah, so if you go to chapter 21, I'll show you. Bear with me here. So if we go to chapter 21, might take me a second to find it here, but it's in here. So if you scroll down to when we talked about the diethylmalonate, so we did aldol additions, condensations, all that stuff, crossed aldols, intramolecular. Then we did clayzin. So we did clayzin this and clayzin that, beta keto esters, all that stuff, alkylation, kinetic thermodynamic. But right here, right, we talked about taking diethylmalonate, right, and then you put an R group in the middle like this, then you hydrolyze it and you make this dicarboxylic acid. So it's the same thing that they had in that compound, right? You had a carboxyl group, then you have a ring, then you have a carbonyl. So this piece is this part right here. And so when you heat that up, what happens is you end up losing CO2. And of course, this proton goes on here, right? Because that proton wasn't there before. So you lose CO2. So that's the decarboxylation. Does that help?
Yes, thank you.
Yeah, no problem. And then I'll show you in chapter 25, it doesn't provide a mechanism, it just kind of refers to it in chapter 25. When we did the amido-malonate synthesis at the very end, if I just skip towards the bottom, you'll see it. Where was the review? What was it, chapter 25? Yeah, it's in here somewhere. Oh, good gravy. Where did I put it? No, it's back here, I guess. Yeah, when we looked at amino acid synthesis, we talked about the amido-malonate synthesis, which is right here. Okay, so you see the same thing occurring here. So we have this portion here, right, which is the same thing as having, sorry, I'm using a yellow pen, but it's the same thing as having a carbonyl and then a carboxyl group attached to it. And then after you heat it, you end up losing the carboxyl group. So you see that right here. Okay, we end up losing all of that piece. Anyhow, so that's the rationale for that one. Hopefully that helps. But that's where that's found, is in chapter 21 mostly, but then it's referred to in chapter 25 as well. So let's go back to from whence we came, which was somewhere, no, we weren't there. We were here. All right. So as long as you know the concept, all you're looking for is two carbonyls that are 1,3, right? This is the only place we have a 1,3 dicarbonyl. This is a 1,4 dicarbonyl, those two. And the same thing, this would be a 1, 2, 3, 4, 5 dicarbonyl. So the only place where they're 1,3 would be where carbon 2 is situated. Okay, let's move on to question number, what did I have next? Question number 21, I think. Yes, question 21 is a good one. All right, what would be the major product of this sequence in question 21? So we're taking this ester here, so this would be ethyl benzoate. So if you draw the bond lines, you have ethyl benzoate, and then this here, this is ethyl propionate. So that is, maybe I should use a different color. So that is this compound, so ethyl propionate. So you can see the only compound here that has an enolizable proton is going to be the one in blue, right? This is the only place because there's no alpha proton or beta proton here because that's an aromatic ring. And so this is the only possibility. So after we deprotonate this, what's going to happen? This is our nucleophile. This is our electrophile. Like this, we're going to do a nucleophilic acyl substitution. And so this is a Claisen reaction. And so all that's going to happen in the end is we're going to end up with, if I use my arrow here, is you're going to have this piece is going to remain completely intact, and all that's going to be attached to the bottom of it at this position is going to be, let me use my red pen, you're going to have your carbonyl, and then you're going to have your phenyl group attached to it like that. That's the whole thing. And you can see that that is compound B, right? They turned this bond around, but it is compound B right here, okay? Attached to the alpha carbon, you have the carbonyl that came from the ethyl benzoate. And so there you have it. So this is our alpha carbonyl, and that would be it. So this would be a Claisen reaction, right? Remember we talked about a beta keto ester? Well, that's what this is, okay? This compound here, right? The beta carbon, you have a ketone, and then here you have an ester. So this is a beta keto ester. Yabba dabba do. Good. All right. Let's see. Number 22. What's that one about? How to win friends and influence people. No, it's got nothing to do with that. It says, what is the starting material that will yield this compound upon treatment with sodium ethoxide in ethanol? So if we take a look at here, this comes from an intramolecular Claisen, which is a Dieckmann cyclization. And so this is our alpha carbon, this is our beta carbon. So that's where we're going to make our disconnect, is we're going to break this apart here. So if we break that apart, and again, I'm kind of running out of space here, but you'd have your carbonyl, you have your ethyl group. Now, if we count these carbons, so we'll go 1, 2, 3, 4, 5, 6. So I'm starting at this carbon, 1, 2, 3, 4, 5, 6, like this. And then we're going to have a carbonyl like this. And then we're going to have our other ester group. So this is the compound that we're going to have. And so if you count, or if you look at these compounds carefully, look between the two carbonyls, and we have a total of 1, 2, 3, 4, 5, 6. And so if you look between the two carbonyls, am I looking at the wrong one? Oh, no, it's this one here. 1, 2, 3, 4, 5, 6. And then you have an ethyl group here, and you have an ethyl group here. And so the answer is going to be D. So this is the Dieckmann. Dieckmann. Am I spelling that right? Is it Dieckmann cyclization, which is, again, is nothing more than an intramolecular Claisen reaction. All it is. You don't, I mean, the main thing is just study the Claisen reaction. Okay. When I took this class back in 1995 or 6, okay, I remember my instructor on one of our exams, they had taught us the Claisen, but they hadn't gone over the Dieckmann yet. And they asked us this question, you know, something along those lines. And what reaction is this? Well, I didn't even know what a Dieckmann was, but I knew what a Claisen was. So I called it that. And they said, well, it's kind of what we were looking for, is just to see if you could figure out an intramolecular Claisen reaction. Let's see here. There happens to be question 27. 27 is this guy here. Oh boy, this one's wild. Okay, we've got an ester, and then we've got this is called dimethyl oxalate. If you remember oxalic acid, you guys remember oh my stars go away? Well, oxalic acid has 2 carbons in it. So if you have this, right, like that, that's oxalic acid. And so this compound would be dimethyl oxalate, is the way you would name that. Okay, so if you take dimethyl oxalate and this compound, so this is methylpropanoate or methylpropionate, either name is fine. You treat it with sodium methoxide, right? This is the same thing as NaOMe. And then acid at the end. Well, what's going to happen? There's only one enolizable proton in here, and it's this one. So we would end up with our enolate here, and then our enolate is going to be able to attack here, right? So we're going to do our nucleophilic acyl substitution over here like this. And so then we're going to end up losing the methoxy group, okay? Because this is the good leaving group, right? This is not a good leaving group. So we end up losing the methoxide. And so what we're going to end up with, if I just draw a brief mechanism here, just bear with me, you guys. So we're going to end up with something that looks like this. So there's our ester. And now we're going to have our nucleophilic acyl substitution. So if I circle this part in blue, we're going to have our carbon with our negative charge. Then we've got our methoxy group. Then we've got the carbonyl, right, like this. So now what's going to happen is our negative charge going to make our double bond, and then we're going to lose this as our leaving group. The alkoxide, right, is going to be a better leaving group. And you're never going to see this, right? This is nothing, okay? That's not a leaving group, never was, never will be. I'm going to erase that so nobody will ever see that I wrote that down. So after the leaving group leaves, what do you end up with? If you look very carefully, what you're going to end up with is compound A. So if you look at compound A, right, count very carefully. You have 1, 2, 3 carbons from your methylpropionate, and then you have this. Let me circle it in green. You have this portion. Sorry, you have this portion here is going to be attached like that. So there you go. And that's just a regular old nucleophilic acyl substitution reaction. Nothing more than that. Okay, let's do one more from this section, then we're going to move on to aromatic substitution. So question number 30 is the last one I had. Why do I always pick these big bruisers here? The questions are pretty long, where you have all the different conditions. Which of these reactions could be used to make this beta keto ester? Well, if we're making a beta keto ester, what kind of reaction are we doing? It's like that new dance sensation. Everybody's doing the Claisen, right? So we need to find Claisen condensation reaction conditions. Okay, if we look at the first set of conditions, there's an enolizable proton here. You do a nucleophilic attack like this, lose your leaving group, and that would that give you the product? No, it wouldn't, because you don't have, you're missing these carbons here. They're not even there. So number one, hold on, what am I missing? Oh, I didn't notice the second step. Mr. Dion needs to pay more careful attention. So there's the second step where you have the ethyl bromide, because I was like, what's that for? Okay, so in the first step, you do the nucleophilic acyl substitution. So you make your carbanion here, right? Nucleophilic acyl substitution. And then after your loss of leaving group, you still do another deprotonation, and then you alkylate using the ethyl bromide, because after the first part of the reaction, shoot, you end up with this ion. You end up with this. There we go. You end up with this, okay? And this is for number one. And then that's going to react with ethyl bromide in an SN2, and that's going to give you the product. So yes, number one will work. In number two, we have our sodium methoxide. We're treating it. We have only one enolizable proton here, so we do that. We do our nucleophilic attack, loss of this leaving group, and yes, that will give us the right product again. So this one will work. And the last one is, remember, this is called a carbonate here. So the only enolizable proton you have in this one is this one here. You deprotonate, it does nucleophilic acyl substitution on this. You lose this part. And in that case, would you get the right product? Yeah, you would again. So all three of these, 1, 2, and 3, they will all give you the same product. Now, there's no question on your exam that has like 3 scenarios for you to go through like this. They're just kind of one question at a time, but it still provides us with some good food for thought here.